This is Mrs. Hayes, and we're doing the 7.2 Features of Exponential Functions notes. So the last video I made, I talked about exponential having this form, a times b to the x, and that's what I'm seeing here in example 1. Our function is 4 times 2 to the x. So if you remember from last video, the 4 is your initial value, otherwise known as your y-intercept, and the 2 is your multiplier. All right, so let's take a look at using this function to generate a table. Let's not use our graphing calculator. Let's use our brains first. I'm going to start here and put a 0 in for x. So I'm doing f of 0, which would be 4 times 2 to the 0. Anything to the 0 power is 1. I know that's weird, but believe me, anything to the 0 power is 1. And 4 times 1 would be 4. So this is a 4. Now I knew that because I already told you that's my initial value and it's sitting right there. And so it works. It's right. Now let's put a 1 in. What would be 4 times 2 to the first power? In other words, f of 1. 4 times 2 to the first power. Well, you have to do the exponent first and then multiply. Anything to the first power is just itself, so you're just doing 4 times 2, and that is 8. All right, let's do f of 2. F of 2. I should have changed pen colors, but hopefully you can still see this. 4 times 2 to the second power. Again, you got to do the exponent first and then multiply by 4. So 4 times 2 to the second power is 4. That'll be a 16. Right now I'm starting to see that there's a pattern that I'm multiplying by 2 and multiplying by 2, and I knew that because my multiplier is 2. So I could either just call this 32 and then multiply that by 2 and call it 64, or I could look at f of 4, for example. It's 4 times 2 to the fourth. So that's 4 times 2 times 2 times 2 times 2. That's 16, and that gives me 64. So that's not too bad with the positives. Let's look at the negatives. What is f of negative 1? That would be 4 times 2 to the negative 1. 2 to the negative 1 on your calculator is going to be 0.5. 4 times 0.5, or also know that it's 4 times 1/2, and that would be 2. So the reverse of multiplying by 2 is going to be to divide by 2. Or just keep using the table or the function. Let's see, f of negative 2 would be 4 times 2 to the negative 2. That means 4 times 1 over 2 squared. 4 times a fourth is 1. That would be a 1. I'm going to erase some junk here. Sorry about this. And I'm just going to put a 1 in the box. If you did 4 times 2 to the negative 3 on your calculator, you would get 1/2. If you did 4 times 2 to the negative 4 on your calculator, you would get 1/4. In other words, you're dividing by 2 as you move through your table this way. Half of a half is a fourth. Half of a fourth is an eighth. Half of an eighth is a 16th, and so on. It's going to get very, very, very close to 0 if you keep going that way, very small. The initial value is right here. It is 4, or 0, 4. The multiplier is 2. As you move this way in your table, you were doubling. F of 2, I already did a whole bunch of these up above, but it'd be 4 times 2 to the second power. There's where your x goes. 4 times 4, yep, 16. In your table, it's right here. The domain, oh, wait a minute, let's do E first. Find the value of x when the function is 2. When the function is 2, your x value is negative 1. X equals negative 1. A, B, C, D, E, F. Okay, now the domain. The domain is, if you keep going, you're going to go, wait a minute, not y values, x values. You could go all the way from negative infinity to infinity. You can keep putting smaller and smaller x values in or bigger x values in. Negative infinity to infinity, it goes this way and that way forever. The range, however, only reaches a low point of 0. The lowest value is 0. The highest value is infinity. It keeps getting 16, 60, 32, 64, higher and higher and higher. So for the range, I would say 0 to infinity. It never reaches 0, so I put a parenthesis on that. Plotting the values now, we're going to start from 4. This goes by 2, so here's 4. And then we're just going to plot these values. 1, 8, 2, 16, 3, 32, and 4 would be off the charts already. And then -1 is 2, -2 is a half, and then a quarter, and it keeps getting closer and closer and closer to this line, but never touches it. The equation of the asymptote then is y equals 0, otherwise known as the x-axis, where y is 0. So y-intercept, the y-intercept is 0, 4, and that relates to the equation. If you remember, it was 4 times 2 to the x, wasn't it? Am I wrong about that? Was this 4 times, yep, 4 times 2 to the x. And there's your 4 from your y-intercept. The average rate of change from 0 to 2, I always make a table when I see that, and I think about the word slope, and I put these x values here, 0 and 2. So on the interval from 0 to 2, my y values are 4 and 16, just looking at your table. So the y values are 4 and 16. That's an increase of 12 when this increased by 2. So my change in y over x is 12 over 2, which is 6. So the steepness of this line going from 0 to 2, this little line segment right here, if you can see that, would be a steepness of 6. Does this function have a constant rate of change? Well, that was 6, but as this function goes on, that's two separate words, I don't know why I wrote them so close. As the function goes on, it gets steeper. So the answer is no. I should have said no first, maybe. As the function goes on, it gets steeper. It's not constant. So here it was a steepness of 6, and then here it would be even steeper, and so on. It gets steeper as it's going up. Steeper than this, steeper than that. So as you move this way, your graph is getting steeper, steeper, steeper. So the answer is no, it is not a constant rate of change, unlike linear, where it's always the same steepness. All right, guys, thanks for joining me. We'll see you soon.